Alright guys, on Tuesday we started talking about reaction types. We know that reaction types we use for observing patterns, and these patterns are what you guys are going to use to predict products today. So remember, there are 5 different types of reactions. We have the combination or synthesis reaction. Remember, we said it was A plus X yields AX. Basically, we have 2 or more substances and it combines to form one new substance. So basically, to identify this, you either have one element plus one element, and it can give us one compound. I'm going to represent compound as CPD. Or we can have a small compound and another compound, and it creates one big compound. You are going to see it in this class mostly like this, okay, where you have one element added together to give you a larger element. This is fairly simple to identify. We don't practice it as much as we do the others. Then we have decomposition. Remember, it is the opposite of synthesis, so we're taking one compound and we are breaking it into 2 or more substances. So if you can remember, I told you guys that you need to remember or memorize these, and let me see if I can zoom in. You need to memorize these different types of problems. So if it's binary, which means only 2 elements are involved, it's going to automatically split into those 2 individual elements. If it's a metal carbonate, so carbonate's present, what's going to happen is the metal and oxygen are going to combine, and then we have one CO2 molecule always, and that's important when we get to predicting products. Same thing with hydroxides. Calcium and oxygen, or the metal and oxygen, are going to combine, and then we have H2O that always comes out. And then metal chlorates, we're going to have the metal and chlorine combine, and then oxygen comes out of it. Oxyacids are going to change. Basically, our acids are going to be different because it's going to form CO2 and H2O. It also depends on what type of acid you put into the equation. And then we got to single replacement. That's what we're going to be working with mainly today when it comes to predicting products. And we have 2 different equations. We have AX plus B yields BX plus A, which is a metal replacing a metal, or a cation replacing a cation. And then we also had AX plus Y yields AY plus X, and that's where halogens are replacing each other. You have to have this memorized. If you do not have this memorized, you are going to be swapping things that you shouldn't swap, or your products are going to end up really weird. So metals can replace other metals. If we see water present, metals can replace hydrogen in water. Okay, if it's an acid present, I can have metals replace hydrogen in the acids, and then halogens, of course, replace other halogens. With this in mind, we can only do certain reactions based off of the activity series. So if you looked at the back of your notes, we talked about this activity series. Metals can replace metals that are lower than them. So if my metal is potassium and it's trying to replace zinc, it can do it. But if I have, say, aluminum and it's trying to replace potassium, it can't do it. And then, of course, metals above hydrogen can replace all acids. So all of these right here can replace acids, but these 4 at the top are the only things that can replace hydrogen and water. You also have to have that memorized. I will give you the chart. You just need to know how to read it. And then you have an activity series for your halogens. Fluorine is the most reactive, so it can replace anything. So we can see here fluorine replaces chlorine and sodium chloride. But if I had bromine trying to replace something like chlorine, which is above it, it can't do it. So if we can't do something, we put no reaction instead of following it through. Okay. Our fourth type of reaction was double replacement. Remember, this is us swapping out the ions. It really doesn't matter which ion you swap out. I like to swap out my anions because it just keeps everything clean. And this is a Y. And this is an X. Remember, this is very important for you to memorize or know for your test, especially when we get to net ionic equations. Double replacements can form precipitates, can form gases, and can form molecular compounds. Right? And then lastly, we have combustion. There's not a general equation, but when we are looking at hydrocarbons, the general equation is carbon with any number for its subscript, hydrogen with any number as its subscript, plus oxygen. No matter what, it's going to give you CO2 and H2O. If it's not being added to a hydrocarbon, anything that has oxygen added to it can be a combustion problem. Just remember, combustion can also be synthesis, so I have these two added together to form one compound. That's also synthesis. Combustion because it's oxygen added. And then, of course, it can also have single replacements as well. Questions over the types, now that I've gone over them. Alright, so you guys were taking part B of your unit sheet, and you were identifying whether or not it was considered combustion, synthesis, or single replacement, double replacement, or decomposition. So looking at Na plus Cl and it forms sodium chloride, what type of reaction should this be? It should be synthesis because I have two different elements becoming one new compound. So you should have put an S next to it. Alright, number 2, I have one compound breaking into two. What kind of reaction is this? Decomposition. What about 3? I have one element plus one compound. Single replacement. So that's something that if you struggle identifying these, single replacement, notice I have an element by itself plus a compound on the reactant side. That is an indication of a single replacement reaction. Okay, so looking back, number 3 is single replacement. I have one element and a compound, so single replacement. What about number 4? Single replacement. I have one element and then a compound. How about number 5? Double replacement. I have two compounds. Usually it's an acid and an ionic compound, and it neutralizes each other. That's usually double replacement. What about number 6? Decomposition. Okay, see, I have one compound here on the reactant side. That's going to break down into 2. Decomposition. What about number 7? It's going to be synthesis. I have 2 little simple compounds becoming one. So that is synthesis. Number 8. Double replacement. I got 2 compounds. Number 9. Single replacement. I have one element, one compound. And then what about number 10? Synthesis. 2 compounds becoming one whole new substance. Alright, questions over how to identify these substances. Alright. Alright guys, using the patterns that we just looked at with reaction types, we can now predict products. And there's not a set of notes that go over this. It's basically technique. It's not a hard technique as long as you follow all the rules. Alright, so for number 1, you have iron 3. How would I write iron 3? Fe. Remember, that 3 is to tell you what oxidation state you guys are going to use when your products come about. So I'm going to put a line out in front of it so I can balance it when I'm done. Alright, the thing about predicting products, it leads us to net ionic equations, and we have to identify what's a solid and what is aqueous. And remember, aqueous is something dissolved in water. When we have metals by themselves, they are considered solid. So I'm going to put an S I always write it in cursive. You can write it in print. So I know that that is a solid piece of iron that I'm working with. And then we have silver acetate. So silver is +1. Acetate is -1 for its oxidation state. Yes?
What did you write? It's not the FB, I can't see.
That's an S, a cursive S. Okay. Acetate is a -1 oxidation state. So when you swap and drop, because it's ionic, both of them are going to have a 1 and 1 subscript. My suggestion is for you, since we are moving things around, is to put your polyatomic ions in parentheses always, so then that way you're not moving something you're not supposed to, okay? And so I gave you a activity series. Now the activity series is useful for my single replacement reaction. So as soon as you identify single replacement, you'll use this. But if you look at the bottom, I have my solubility rules. And this is going to determine what state you put next to the compound itself. We are only going to use the ones on this table. Anything else, if it's not on this table, you are not going to write the state next to it, okay? So notice for silver acetate, I don't have silver or acetate on my ion chart. So I am not going to add a state right here because that's not going to be anything you have to predict in this class, okay? All right, so now we are predicting products. When we are predicting products, the first thing you need to figure out is it going to be single replacement, double replacement, synthesis, decomposition, or combustion? What type of reaction would this be? Single replacement, because I have one element and a compound being added together. So when I say single replacement, I automatically know to look at my activity series right here. All right, so the one by itself has to be higher than the one that is in the compound. And remember, you have to figure out which one you're replacing. So remember, it's metals and metals, metals and hydrogen, and halogens and halogens. So what two are present here that I'm going to swap out? A metal and a metal. Okay, everyone understand? Iron and silver are the only two metals, so they have to be replacing each other. So I look, iron is right here, and then silver is all the way down here. So can you see how iron is higher, which means it can take over and replace silver. So what I'm going to do is now I'm going to have silver by itself, and no, it does not matter which one or which order you put it in. I'm going to do silver first, and since silver is by itself, I don't consider its oxidation state. I do know because it's a metal by itself, I can put S next to it because it's a solid. And then iron is now going to be paired with acetate. And I'm going to write down the new combination, and then I'm going to come in and add subscripts afterwards. Okay? So iron had a +3 oxidation state, and I'm going to do some scratch work up here. And then acetate, we know, has a -1 charge. So we are going to swap and drop. Iron gets this 1 as its subscript, and you don't have to write the 1 unless you want to. And then now acetate gets a subscript of 3, and it's still that same swap and drop method. Okay? Questions over how I swap them out. Your subscripts never travel to the other side. Remember, subscripts rely on oxidation state, and so you have to keep on swapping and dropping on both sides. And then now we can balance. And balancing should be pretty fresh on your mind from yesterday. So I have iron, I have silver, and I have acetate. Okay. I know that I had 1 iron and 1 iron on both sides, 1 silver on both sides. Reactants, I have 1 acetate. Products, I had 3. So you have to change the reactants by multiplying it by a 3. When I multiply this side by a 3, what did I do to silver? I changed the silver's reactant to 3 by multiplying it by 3. So I can multiply my product side by 3 and it's fixed. So I have a 1 to 3 to 3 to 1 ratio, or if you flip these, it's a 1 to 3 to 1 to 3 ratio. On your test, I will look at whatever order you put it in as long as you have the correct products and the correct reactants. Okay? Questions over number 1. Alright, number 2, we have calcium chloride. Calcium is represented by Ca. Chlorine, of course, is Cl. We know calcium has a +2, chlorine has a -1, so when you swap and drop chlorine, it gets a subscript of 2. Real quick, let's look at our solubility rules. Okay, when I have chlorine present, it is soluble unless it is mixed with lead, silver, or mercury. So it's not mixed with any of those, so it's soluble. When something is considered soluble, I write AQ to show that it's dissolved. Alright, and then it says sulfuric acid. You remember ic was 8, so I'm working with sulfate. Sulfate should be H2SO4. And then I look to see if I can write a state for it. SO4 is soluble unless it's paired with calcium, barium, strontium, lead, silver, or mercury. And so it is not paired with any of those right now, so that means it's aqueous. Most acids are aqueous. Alright, so now it's time to predict products. What type of reaction is this? This is a double replacement. So with double replacements, we do not worry about the activity series. Double replacement is going to follow through no matter what, and it's because we're switching ions. I like to switch anions because I know I can keep my polyatomic ions under control. So I know that the anion here is chlorine, so I'm going to color code it so I know what I'm moving. Okay, so Cl. And then SO4 is my anion over here, so this is what I will move on this side. So these two things are swapping places. So now instead of calcium chloride, I'm going to have calcium and sulfate together on this side. So Ca, SO4, and then I take into consideration their oxidation states. Calcium has a +2, sulfate has a -2, so it's just a 1-to-1 ratio. Right, now hydrogen is no longer with sulfate, it's with chlorine, so it's HCl. They both have a 1 oxidation state, so it is 1-to-1. Right, now we can add their states in with it. We know sulfate is going to be soluble unless it's paired with calcium or barium or strontium. It's paired with calcium, so since that is an exception, when one of the exceptions are present, that means it's the opposite. It's no longer soluble, it's considered insoluble. So that means I'm going to put an S here because it is a solid. And then, then looking at hydrochloric acid, I see chlorine present, which means it's soluble, so I'm going to put AQ right here. Real quick, remember what I just said in your notes about how double replacement always forms either water, a molecular compound like water, or an insoluble gas or a precipitate. This double replacement formed a precipitate. Here is our solid, and you will actually see an experiment, or you will see a reaction like this in your lab next week. Okay. All right. So with that in mind, now you just balance it out. And you guys have your balancing chart. I'm going to do it just off of the top of my head. Alright, I have 1 and 1 calcium, that's good. I have 2 chlorines here, so what do I need to put right here? A 2. And then I have 2 hydrogens, I just made this a 2, that's good. 1 sulfate, that's good. So it's a 1-to-1-to-1-to-2 ratio. Questions over this? Alright, not that hard, right? Shouldn't be that hard. Alright, so numbers 3 and numbers number 4 are going to be similar to what we just did. So go ahead, do 4 and 5, and we're going to come back together in just a second. Alright, so hopefully when you started writing the reactants, iron 3 hydroxide looks like this. It is considered a solid, okay, because hydroxide is insoluble on your chart. Then I have phosphoric acid. Phosphate, of course, when present, is usually insoluble, but because hydrogen is present, it makes it aqueous. So with that in mind, what type of reaction is this? A double replacement or double displacement, okay? So I'm swapping out ions. So it is your choice on if you move the cations or if you move the anions. I always swap the cations. Okay. And remember, subscripts do not travel unless it's already part of the polyatomic ion. So iron is now going to be paired with phosphate. So iron was a +3, phosphate we know is a -3, so it's a 1-to-1 ratio. We don't have to add any subscripts, and we know that if we look at our solubility rules, we can see phosphate is going to be insoluble, so this is a solid. And then now hydrogen is combined with hydroxide. It's a +1 and a -1. Okay, so a lot of you probably wrote it like this. I need you to understand that this is H2 and an O. So this is water. Anytime you see a hydroxide ion and a hydrogen ion come together, it's considered water. I'm going to put its balancing line right there. And then the only liquids we will ever see is water. Okay, water is not dissolved in anything. Water is a solvent, so it's considered a liquid. That being said, now you can balance it. I have iron 1 and 1. Okay, phosphate 1 and 1. So then let's look at the H's and the O's. I have 3 hydrogens here. I have 3 hydrogens here. So that's 6, which means I have to put a 3 over here. And then I have 3 oxygens right here, which I just put a 3 here, 3 oxygens here. So it's a 1-to-1 to 1-to-3 ratio. Okay? Yes. So let me see if I can get this paper to show that I was balancing. Okay. So if I had Fe and I had PO4, I had H, and I had O. It was 1 and 1, 1 and 1. So originally, hydrogen, I have 3 right here, plus the 3 on the acid, so that gave me 6. I originally had 2 right here, and to make 2 a 6, I have to multiply it by 3, and that's where I get this coefficient. Oxygen, this 3 applies to oxygen as well, so I have 3 right here, and we just placed a 3, so that fixes it. If you put that 3 here for oxygen originally, it'll fix hydrogen right away. Yeah, parentheses always is a helpful tool to avoid that. Alright, number 4, we had silver nitrate, which is a +1 and -1. It comes together, it's 1-to-1. If you look at your solubility chart, we know that nitrate is going to be soluble always. So we put AQ next to it, and then we've already established that CaCl2 is aqueous as well. What type of reaction is this? It's a double replacement, okay? So we don't have to use the activity series for this. So what I'm going to do is I'm going to swap out my anion. So if you like to color coordinate, NO3 stays together, Cl stays together. I don't carry any subscripts with me. So silver is now paired with chlorine, and they both have a 1 as their oxidation state, so they neutralize each other. And if I look at chlorine, it's soluble except for when lead, silver, and mercury are all combined with chlorine. So that means instead of being soluble, it's going to be insoluble. So I put an S here, and that's going to be our precipitate. And then now calcium is going to be paired with nitrate. Remember, calcium has a +2, nitrate has a -1, so I get a 2 as a subscript for nitrate. And then remember, nitrate is always soluble, so this is aqueous. Okay? So then when you are balancing this out, okay, I have a 1 and 1 silver. Nitrate, I have 1 whole nitrate here, but I have 2 here, so I have to put a 2 over here, which makes me have to fix silver over here to a 2. And then, of course, calcium, it's 1 and 1. Chlorine is 2, and then the 2 here. So it's a 2 to 1, 2 to 1 ratio. Questions? Yes?
Does it matter the order? Like, do we have to
Put this first?
Yeah.
No, it doesn't. So then your ratio will read 2 to 1 to 1 to 2. So if I'm asking for the ratio, normally I will put the words in order the way I want you to write it. But regardless, I will now be looking for your ratios in different arrangements, so it's not going to matter. All right, we have strontium iodide. Strontium is Sr with a +2 oxidation state, iodine -1. When you swap and drop, iodine is going to get a 2 as its subscript. It is being added to chlorine gas, which we know is diatomic, so it gets a 2. If we looked at strontium iodide, when iodine is present, okay, it is going to be soluble unless these 3 elements are present. So we will consider this compound aqueous. And then chlorine, all the diatomic molecules, we consider a gas. So we'll put a G next to it. Right? What type of reaction is this? Single replacement. Okay? So with single replacement, I have to use my activity series. So I'm going to look. What is going to replace what in this reaction? Is it metals and metals, metals and hydrogen, or halogens and halogens? Halogens and halogens. So we can see our non-metal chart right here. Chlorine has to be higher than iodine to replace it. Is chlorine higher than iodine? Yes, so this can follow through. Strontium is now going to be paired with chlorine. Strontium has a +2, chlorine has -1. So when you swap and drop, it becomes a 2. And this is considered aqueous because chlorine is present. And then iodine is by itself. That is going to be a gas. We put a 2 next to it because it's diatomic. Yes.
How do you know that, like, iodine is going to pair with? Or how do you know that it's 2 halogens?
It's 2 halogens because there's not 2 metals present. Like, you have to identify the element classes. You also can think oxidation states. So I know strontium would have a positive, iodine has a negative, and chlorine has a negative. So negative can replace negative, positive can replace positive. Okay. Strontium, it's 1 and 1. Iodine, it's 2 and 2. Chlorine is 2 and 2. So this problem is already balanced. Okay, so it's a 1 to 1 to 1 to 1 ratio. Questions? How are we feeling? Good. It just takes practice. It's very tedious. Okay. I want to show you one that's a little bit different, and then I'm going to have you flip over to the back before we finish this sheet so then I can stop making my video. Everybody skip to number 8 real quick. I have aluminum, which is Al, and it's S, or a solid, because it's by itself. I have potassium chloride, which is a +1 and a -1, so they get no subscripts, and it's going to be considered aqueous. And I tell you guys to predict the products, but first you have to identify the reaction type. What's the reaction type for this? Single replacement. So I pull out my activity series. What is going to want to replace what in this reaction? Aluminum is going to want to replace potassium. So it's a metal and a metal. So aluminum by itself has to be higher than potassium. Is aluminum higher than potassium? No. So what do I write for this? Good. And so then before we finish up the sheet, this sheet just shows you single replacement and double replacement, and it shows you the exceptions and it helps you with the states. But you guys also need to understand how to do synthesis, combustion, and how to do some decomposition. So flip over to the back of your sheet, or you can write this on your notes. We are going to first look at what happens if I gave you an example that says magnesium reacts with oxygen. And I tell you to predict the product. So I draw an arrow. All right, we know magnesium is Mg, and it is going to be a solid because it's a metal by itself. We know reacts has the plus sign, and oxygen is considered a gas, and it's diatomic, so it gets a subscript of 2 automatically. All right, so technically this is considered a combustion reaction because oxygen is present, but I am going to use it to show you synthesis mainly. Remember, some combustion is synthesis, or some synthesis is combustion. So I have one element and one element coming together, and that's going to show you synthesis. So we are just pulling them together or adding them together. We have Mg and O, and you just consider oxidation states. Magnesium has a +2, oxygen has a -2, so it's a 1-to-1 ratio. So this is synthesis. Okay, we have to put a 2 here and a 2 here to balance it out, and it's good. I would identify this as synthesis, or I would take combustion if you put combustion. Right, synthesis should be easy because you're just taking two things and combining it together. The synthesis, I will never give you 2 small compounds and have you create 1 big compound. I'll always give you the product for that. So questions over synthesis. All right, let's look at something that would say C2H4 plus oxygen, and that's how you would see it in its word form. I'll never give you a hydrocarbon in word form. Okay, so we know that if we brought this down, it's this hydrocarbon, dicarbon, tetrahydride being added to O2. We know that when oxygen is being added, this is considered a combustion problem. And when something combusts with oxygen and a hydrocarbon is present, we always will have CO2 and H2O form. That's the simplest version, or simplest reaction type to predict products. I see a hydrocarbon, I see oxygen, automatically CO2 and H2O. And then you just balance. I have 2 carbons here, put a 2 here. 4 hydrogens here, 2 here, so I'll put a 2 here. And so then oxygen, 2 times 2 is 4, plus the 2 right here is 6. So then how can I make this a 6? Multiply it by 3, and there you go. I have a 1-to-3 to 2-to-2 ratio. All right, questions over combustion. All right, the real issues we see is when we see decomposition. So I'm going to show you 2 examples of decomposition. Hang in there. I'm almost done. You're fixing to practice on your own. All right, if I gave you magnesium, let's see, magnesium carbonate by itself. And I said, predict the products. First off, you'll want to write the skeletal form, Mg +2, CO3 -2, so it's a 1-to-1 ratio. If you look at your solubility rules, CO3 is insoluble except for group 1 and NH4. Mg is not group 1, so this is considered insoluble. It's a solid. So I'm going to predict products. So I told you guys you got to remember the patterns from your notes. Usually I'm going to use the examples from your notes, or the examples I'm showing you now. Those are the only ones you're going to see in this class, because anything beyond that is AP chemistry or college level chemistry. Okay, so if I look carbonates in your notes, I said forms a metal oxide and CO2. So I know CO2 should be in my products, and CO2 is the gas that I normally work with, or the only gas I'm going to be working with you guys, along with my polyatomic ions. And then it is going to be the metal and oxygen. So I have Mg and oxygen. +2, -2, so it's a 1-to-1 ratio. And this is usually a solid as well, but because this is not on our solubility chart, we're not going to worry about putting its state, just like hydrocarbons. Hydrocarbons are normally gases, but because this is not on our chart, I'm not going to worry about it. I do know that CO2 is a gas and H2O is a liquid, but other than that, I wouldn't expect you to put the states for those. Alright, so this is how you do decomposition of a carbonate. And then you would balance it like normal. Okay, I have 1 Mg, 1 Mg, 1 C, 1 C. I have 3 oxygens, 3 oxygens, so it is balanced. Normally I will give you a balanced one already. And then I want to show you another one, because not all decompositions form the same thing. If I gave you sodium chlorate, and I told you to decompose this, sodium's Na, chlorate is ClO3. It's a 1-to-1 ratio chlorate. If you look at your solubility rules, it is not on there, so we're not going to put a state for it. With our carbonates, or not our carbonates, our chlorates, if you look back at your notes, chlorate is always going to form the metal and chlorine and oxygen. So my metal and chlorine is NaCl, so table salt. And usually this is going to be solid or aqueous. Okay, looking at solubility, it's aqueous. And then oxygen always comes with chlorates as well. This one you will have to balance. Chlorates usually cause balancing because of oxygens. So I'm just going to put my subscript as my coefficient for oxygens. This 2 over here is going to become this coefficient. This 3 is going to become this coefficient that balances out oxygen. And then sodium chlorides by itself, I can fix that by simply putting a 2 here. I have a 2-to-3 ratio. Questions over those 3 different types of predicting products? I am mainly going to focus on single and double replacement. They're the easiest, and synthesis, because you guys can add elements together. But no, decomposition, of course, is fair game when it comes to the ones I showed you, not any other ones that are new. And combustion, if we have a hydrocarbon and oxygen added together, it automatically forms CO2 and H2O.